In this video, we're going to learn about two specific scalarization methods for solving multi-objective optimization problems. We're going to start off with an overview of multi-objective optimization problem properties. We're going to have an overview of solution strategies. First, we're going to dig into the weighted sum method, and then we're going to go through the Epsilon constraint method. Finally, we're going to walk through an example problem demonstrating both methods, including going through the Matlab code that solves the problem using both methods. Multi-objective optimization problem properties. Real design problems often involve more than one objective or more than one metric we want to minimize or maximize. For example, if we're designing a car, we'd like to maximize fuel efficiency, acceleration performance, but do all of that while minimizing cost. Practical multi-objective optimization problems have conflicting objectives. There's a trade-off between these objectives. For example, usually if we design a car that has both improved fuel efficiency and improved acceleration, it's going to cost more. Specifically, if we have two or more conflicting objective functions, to improve one of these objective functions, it often requires giving something up with another objective function. A solution to a multi-objective optimization problem quantifies the trade-offs between these conflicting objectives. So, for example, more fuel-efficient cars tend to be more expensive than their less efficient counterparts. A problem with non-competing objectives is what might be called a degenerate multi-objective optimization problem. That is, it does not make sense to formulate this problem as a multi-objective problem. And we'll go into this in some more depth a few slides later to see specifically why the term degenerate makes sense. Let's look at a general multi-objective problem formulation. Here we're using again a nonlinear programming model for our optimization problems where we have continuous optimization variables and continuous objective and constraint functions. Here we're looking at minimizing a set of objective functions simultaneously. Another way of looking at this could be to express our set of objective function values as a single vector-valued function. We cannot define optimality conditions for problems with a vector-valued objective function. We produce set-valued solutions for multi-objective optimization problems, and we call this set of solutions either the Pareto front, the Pareto frontier, if we're talking about the solutions in the objective function space, or we call them the Pareto set if we're talking about the solutions in the design variable space. In this solution process, we are searching for what we call non-dominated points. And a non-dominated point is one where we cannot improve one objective function without degrading at least one other objective. Here's one abstract way of thinking about multi-objective optimization. Down here in the left, we are looking at the design space or the optimization variable space. Suppose we have two optimization variables, x1 and x2. And if we have an inequality constrained problem, we need to satisfy all of these inequality constraints simultaneously. If we were to visualize where each of these constraints intersects the zero plane, and suppose we have three constraints, then the set of points that is on the feasible side of each of these intersections is going to be the feasible domain. So here we're going to define F as the feasible domain or the feasible set of points. And then we can think of our objective functions as a mapping from this feasible domain in the optimization variable space to the objective function space. Now switching over, looking at this objective function space, we have what's called the attainable set. The attainable set is the set of all points in the objective function space for which there exists a point in the design space that maps to it. If we are outside of the attainable set, then that means that there exists no value of x that is feasible that will produce the point in the objective function space that's outside of the attainable set. So the designs that we can actually achieve and satisfy all of our constraints correspond to the attainable set here in the objective function space. And here, if we're wanting to minimize both of these objective functions, f1 and f2, we're wanting to move generally toward the origin, down and to the left. So it's desirable to be along this bottom left edge. And this is what we call the Pareto front. And if we have a point on the Pareto front right here, we can see if we're trying to minimize both of these points simultaneously, I cannot reduce one of the objective functions without requiring an increase in the other objective function if I'm to remain in the attainable set. So for example, if I'm at this point right here, and if I try to reduce f1 and move down, all of a sudden I jump out of the attainable set. But to keep this value of f1, what do I have to do? I can move over to the right, and at this point I have a value for f2 that is larger than where I started, so I gave up some performance with respect to objective function 2, but I got back to the attainable set and I improved f1. So all of these points along this lower left curve, these are Pareto optimal points, or these points comprise the Pareto frontier. Let's look at a simple conceptual example. Suppose we are designing an automotive suspension system. We've assumed some configuration. Here we have a short long arm suspension, or it's a 4-bar mechanism, and we're maybe tuning things, continuous variables, things like the link lengths in the linkage system. Or maybe we are tuning things like the properties of the spring or the damper. And these different design decisions will have an influence on how this automotive suspension performs. Two of the metrics that we're typically interested in with an automotive suspension include handling and comfort. And there are a variety of different ways of quantifying handling and comfort. Here we have some very simple ways of quantifying it. Here we're looking at the variance essentially of the contact patch force. If we have a more consistent force at the contact patch, then that tends to improve handling characteristics. And then with comfort, one way of quantifying this is to look at how much acceleration is transmitted to the occupants. And so these are two different scalar measures that allow us to quantify these two different performance metrics. We'd like to reduce both of them simultaneously. These are conflicting objectives. If we have a given suspension configuration like this one, and if we are optimizing the design of this and we find our way to the Pareto front down here, and if we want to improve, say, the handling of the car, that usually means we're going to have to give up something with respect to comfort. So we can have a car that handles well, but it's going to have a stiff ride and it's not going to be as comfortable. That's with the typical automotive suspension technology. Let's have a look now at some broad classes of multi-objective optimization solution strategies. Here are the general solution strategy types. One is scalarization, and the other is direct solution using typically population-based algorithms. Some examples of scalarization include the weighted sum method. This is one that we're going to go through in some detail today. And then compromise programming. This can overcome some of the drawbacks of the weighted sum method, but it also has some drawbacks of its own. So for example, it can increase the level of nonlinearity of an optimization problem. Finally, there's the Epsilon constraint method. We're going to go through this in detail. This is really the most recommended method for your use in this class. Direct solution method examples, at least one, includes the multi-objective genetic algorithm. Here we have a whole population of designs, and this population is changing through the generations, and because we're looking at many different designs simultaneously across a population of designs, we can move toward non-dominated points through this process. Let's talk about scalarization in general. If we are starting with a multi-objective optimization problem that we cannot solve using optimality conditions directly, we can take an approach where we convert a multi-objective problem into a set of single objective problems. And this is the approach that we're going to focus on today, both with weighted sum and with the Epsilon constraint method. We use some parameters to perform a formulation transformation between the multi-objective problem and a single objective problem. We do a parametric sweep across values of these parameters, and each unique set of parameter values is going to give us a unique subproblem. Here I've just denoted these sets of parameters as P1, P2 up to PNP, where NP is the number of parameter values or the number of Pareto optimal points that we are solving for. For example, one way of thinking about this is to vary the importance of each individual objective function. We can weight different objective functions differently. There are other systematic strategies that can be used. Let's have a look at this general idea. We are sweeping through parameter values and using these parameter values to take our multi-objective problem and transform it into a whole set of single objective problems. Suppose we start off with P1, and it gives us this transformed objective function and possibly transformed set of constraints, and I'm labeling this as P1 to make a distinction, and this is a single objective problem. And then we vary the parameter values, we get P2, we get another subproblem, and so on until we have completed going through all of the different sets of parameter values. And so here we have problem number NP. Then we want to solve all of these. Now remember, when we are solving a multi-objective optimization problem, we are wanting to produce a set of points. Each one of these subproblems is going to produce a single point in the Pareto set. If we are looking in the objective function space, it's going to produce a point that is on the Pareto frontier, assuming that the problem was solved, the subproblem was solved successfully. So for example, suppose if we solve this first subproblem and it produces a point here on the Pareto frontier. And then we solve the second subproblem and maybe puts a little bit more emphasis on the objective function corresponding to the vertical axis. We want to minimize that more. And so we move down on the Pareto frontier and we get this point until we solve all of the subproblems and get NP number of Pareto optimal points. What if a subproblem solution fails? Optimization solution algorithms are not bulletproof. It is possible for them to fail. So what are the different ways that optimization algorithms, such as those behind Fmin-Con, terminate? You might remember we went through these termination conditions. The ideal is where we have, in fact, found a local minimum. Or we could terminate because we've reached the maximum number of iterations, or because the objective function or the optimization variable values converged, and there are some other options as well. But there are many different ways that we can terminate without having actually found a local minimum. What might we see in the Pareto frontier if one of these subproblems does not give us an optimum? What if it gives us some other solution? Let's have a look at what this might look like. So back to this Pareto frontier, we solve subproblem 1. It's successful. It gives us a non-dominated point. and subproblem 2 gives us another non-dominated point. But what if subproblem NP has some problems, it does not give us a local minimum, and it produces a point that actually is dominated? It is not a Pareto optimal point. It's important to be aware of this possibility. If you observe points in your resulting set of solutions, then it's important to check the details behind this corresponding solution attempt. You need to do some solution analysis. If something appears to be an anomaly, this is a red flag that you need to do some digging. And in this case, maybe you go back, you try to solve this anomalous problem again. You record things like the exit flag or other properties so that you can do some solution analysis and maybe go back and adjust things in some way, maybe do some better problem scaling so that we can get a better solution for this subproblem. Are there other possibilities, things that could be problematic here? One is that if we're using gradient-based methods, and in general we are solving non-convex optimization problems, then there's the possibility that we will find a local minimum that is not a global minimum. And what if we have a set of subproblems where we are finding the global minimum, but then as we adjust the problem, we adjust these parameter values, we produce a subproblem where it's changed just enough that maybe that minimum disappears, or maybe we jump to a different local minimum. In any case, it goes to a totally different part of the design space and produces a point that just doesn't make sense. And so if that's the case, if we found a local minimum, but we could have found a better local minimum that was a global minimum that would make more sense looking in the objective function space. Or in other words, it actually would be a non-dominated point. If that's the case, then we need to go back and address this anomalous subproblem again and perhaps use a more robust solution approach. There are ways of improving the probability that we find a global minimum, things like a multi-start strategy or a hybrid strategy where we start off with a genetic algorithm to do a broad search, and we use the result of the genetic algorithm for the single objective problem as a starting point for the gradient-based method, and then that improves the chances of us finding the global minimum for that particular subproblem. With that background, let's look into specific scalarization methods. We're going to start with the weighted sum method, and this is the conceptually easiest one to wrap one's mind around. The basic idea is we are using a linear weighting to quantify the importance of the different objective functions in a problem. We're going to form an aggregate objective function using a linear combination of all objective functions. Here's one possible formulation. Say we have two objective functions, here labeled as mu1 and mu2. And then we have these two weights, w1 and w2. If w1 is greater than w2, then that is a way of modeling that mu1 is more important than mu2. This really only captures one set of preferences, w1 and w2. These things could change. Then it's going to give us a different solution that reflects a different set of preferences. We're going to be looking at this conceptual figure from the textbook that shows us how the weighted sum method allows us to traverse through the problem space. And here we're visualizing in the objective function space. And remember, this is very different from how we conceptualize things in the design or the optimization variable space. So the vertical axis here is the second objective function. Horizontal axis is the first objective function. A given value of weights corresponds to parallel straight lines of the same slope for this bijective problem. Two objective problems, we can visualize the objective function space as a plane, and there are analogies to problems with more than two objective functions. What does this mean a little bit more precisely? We're talking about iso cost line. So if J is our cost or aggregate objective function that is formed by taking a linear combination of the two objective functions. If we have these constant weights, we can then in the objective function space look at what the iso cost lines look like. And it turns out that these iso cost lines, if we try to find all the points for which, say, J is equal to 10, that turns out to be a straight line with a particular slope, and that slope is dictated by the values of the weights. We can then move to a different iso line here where J equals 5, but we still have the same slope because the weights have not changed. In choosing W, let's think briefly about the number of degrees of freedom that we have in choosing W. And this is important as you actually go to code something like the weighted sum method, because you need to sweep over these different values of W. In this problem, we have two different weights, W1 and W2. You might think that, well, we have 2 degrees of freedom in choosing the weights, but it actually turns out that it's very typical to use a normalized weighting strategy such that we require all of the weight values are between 0 and 1, and that the sum of these weight values is equal to 1. With this constraint that the sum of the values is equal to 1, that reduces the number of degrees of freedom to n minus 1. So if we have n objective functions, or in this case 2 objective functions, then we only have 1 degree of freedom in the parameter space to sweep through. And it turns out that just with this 1 degree of freedom, we can vary the weight in a way such that we can access the Pareto front, or at least all of the points that are accessible by the weighted sum method can be accessed using a sweep across just a single dimension of weight parameters. Now let's visualize what this looks like. Let's suppose we set some weighting parameters such that this is the slope of our iso cost line. And this is the direction of minimizing cost for a given weighting. And here's another direction, a new value for W that produces iso cost lines with different slopes. We want to minimize the aggregate objective function for different weight values to produce different points on the Pareto frontier. As we sweep through one particular set of values for the weights, that's going to give us a subproblem. We solve the subproblem, and that's sort of like moving the iso line that has a slope for a given set of weights down toward the left and keep going until you can't go anymore without leaving the attainable set. What are the formulation transformation parameters that we are varying and creating a set of single objective problems? Just thinking back to the very general description of scalarization methods that I gave earlier, here we're talking about these different p values. And it should be pretty clear that in this case, it's the set of weights that we are varying. These are the formulation transformation parameters, or in other words, as we change the value of the weights, we use those different values of the weights to take our multi-objective problem and transform it into a single objective problem formulation. Decreasing the aggregate objective function for a given value of W moves us toward the Pareto frontier. Let's visualize this again. Here's our attainable set. If we set the first weight for a bi-objective problem to 0, then the iso cost lines are parallel to mu1, or parallel to the first objective function. We can visualize that here. If we set W1 equal to 0, this is going to be the iso cost line. And if we're trying to minimize J, then moving down is going to be decreasing J. And then if we keep going and moving as far as we can go without leaving the attainable set, this is the result. This is the smallest possible value of J for W1 equals 0. We reach this point. This is the point in the objective function space that results when we solve the subproblem that was produced using W1 equals 0. This is labeled as M2. Specifying W1 equals 0, that produces M2. And M2 is a special type of point. When we set this weight to 0, then that means it ignores the importance of mu1. So it's basically saying it's okay for us to increase mu1 as much as we need so that we can reduce mu2. M2 is called an anchor point, and the anchor points describe the extremes of the Pareto frontier. An anchor point is the point you get where you try to minimize one of the objective functions while ignoring all of the others. Let's have a look at what happens when we set W2 equal to 0. In this case, we get a vertical line, and this is then parallel to the mu2 axis. And if we want to reduce the aggregate objective function value, we need to move to the left. We move to the left as far as we can go. This is what results. This is the smallest possible value of J4. This should be W2 equals 0. And this is the point that we get, the smallest mu1 value point in the attainable set. And that's M1. And M1 is also an anchor point. These anchor points are important, and if we were to take these anchor points and project their values onto the different axes, the intersection of those projections, that would be called the utopia point. The utopia point is the point in the objective function space that represents the best possible objective function value across all of the objective functions, but it usually cannot be attained for a realistic multi-objective optimization problem. If this point over here, where the anchor point is, if that was in the attainable set, then we would not have conflicting objective functions. And this is what we would call a degenerate multi-objective optimization problem, because then the Pareto front, it degenerates into a single point. It's no longer a set of points with more than one value. It's just a single point in the objective function space. All other values for the weights, besides setting the different weights to 0, are going to produce non-dominated points that are in between the anchor points M1 and M2. Let's think through what happens if we change the weights and we change the slopes of these lines and find out what point on the Pareto front a particular slope is going to produce. And here's one, here's another, and all of these are in between the extremes. The weightings that correspond to these slopes are in between the extremes of setting W1 equal to 0 and W2 equal to 0. We need to vary the weights systematically such that they vary between 0, 1, and the sum is equal to 1. This is something that can be done programmatically in a fairly straightforward way using things like for loops, or if you're in Matlab, there are other tricks that you can use to improve the computational efficiency besides for loops. The weighted sum method really is a conceptually easy approach, and it does have the advantage of maintaining linearity. This can help to produce subproblems that tend to be easier to solve than other methods like compromise programming. But are there shortcomings? Absolutely. Let's go through them. The weighted sum method can produce unevenly distributed sets of non-dominated points in the objective function space. What do I mean by that? Essentially, we can get clusters. So even if we are varying W in a uniform manner, it does not necessarily correspond to an even distribution of points in the objective function space. And maybe this is okay. If your distribution is just a little bit clustered, you can still get a good sense of the trade-offs involved. But what if you have huge gaps it may not be adequate for understanding the trade-offs involved with your problem, and you're going to need to fill in some of these gaps with additional non-dominated points. Another issue is that the weighted sum method is completely incapable of finding non-dominated points that are in non-convex regions of the Pareto frontier. So in this attainable set, it is a non-convex set. If we try to draw a line from P to Q, that line exits the attainable set. So this is a non-convex set. The weighted sum method, it turns out, cannot find points on the Pareto frontier between points P and Q. Here's an example of points that the weighted sum method can find, but here are non-dominated points that it can't. If we look at each of these points and think through it, and identify whether it actually is a non-dominated point or not, we try to move in one direction or the other direction, and in either case, we leave the attainable set. So yes, all of these red points, these are non-dominated points, but the weighted sum method is completely incapable of finding them. So why is that? And what kind of impact might that have? Well, if we can't find these points, then we're only going to see this little cluster over here and this little cluster over here, and we have no idea what's going on in between. We don't have a quantitative understanding of the trade-off between the two objective functions. If we are at point P and we look at the line that is tangent to the attainable set at point P, this is going to correspond to the weights that are required to find point P using the weighted sum method. Here, if we look at another point that is down and to the right of Q, we can use the same approach to see what is the isocost line slope that must be used to find that point. If we have non-convex regions in our attainable set that are on the Pareto frontier in the objective function space, then there does not exist a value for the weights that allows us to find a point in this non-convex region during minimization. So for example, point T, that is in this non-convex region. If we were to take a line that is similar in slope to the one that we use to find point P, if we just rotate it a little bit counterclockwise and try to move it down, we need to move down and to the left if we're going to try and find a non-dominated point. If we get to T, well, we're going to keep going because we can keep moving down, we can keep decreasing J, we can move to smaller iso-cost lines without leaving the attainable set. We'll just keep going until we get to point Q. So using the weighted sum method, as we're adjusting the weights, we can find points over here, but then as we get to point P, just as soon as we go slightly beyond the slope that leads us to point P, we're going to jump all the way over to Q, and we're going to skip over all of these points in the non-convex region. That's a very big shortcoming, especially if we keep in mind that when we're solving a multi-objective optimization problem, we don't know ahead of time what the attainable set looks like. Typically, unless it's an already understood, well-known problem, we don't know what the Pareto frontier is, and so we don't know if it's going to be non-convex or not. So we need methods that allow us to find non-convex regions. The compromise programming method is one, but it does have an issue with increasing the nonlinearity of the subproblems. Also, the ability to capture the points in non-convex regions using the compromise programming method is highly dependent on the curvature of these non-convex regions and the exponent that we're using in the compromise programming method. It is possible that if the curvature in the non-convex region of the Pareto frontier is too significant, it's too large a curvature, And if we have a small exponent value in the compromised programming method, it is possible that this method could also miss points in the Pareto frontier. Let's have a look at the epsilon constraint method. This maintains linearity, but it also is capable of finding all points on the Pareto frontier, at least for the class of problems that we're talking about. The basic idea is to convert all objectives, except for one, to constraints. And we put bounds on these constraints. And we systematically vary these bounds on constraints to generate new non-dominated points that are part of the Pareto frontier. This is not an aggregate objective function method. We are not combining all of the multiple objective functions into a single objective. We're only choosing one of them, and then we are reposing those objective functions, the remaining objective functions, as constraints. There are a number of advantages here. We can very reliably identify non-convex regions of Pareto frontiers as long as we can solve the subproblems reliably. Think back to the earlier example where we discussed what might happen if a subproblem does not find a minimum. Well, then that's a case where even the epsilon constraint method could fail to identify a non-dominated point, whether or not it's in a convex or a non-convex portion of the Pareto frontier. Depending on a few different factors, the epsilon constraint method tends to produce a fairly even distribution of points on the Pareto frontier. This really depends on the slope of the Pareto frontier curve in the objective function space. It preserves linearity, and it's generally the most preferred solution method, at least in this class of the methods that you learn. If it's not specified to use something else, use the epsilon constraint method. It's just the most reliable of the methods that we are covering in class. Now, just a quick reminder of what the general scalarization strategy is. We're starting off with a multi-objective problem. And with any scalarization method, we are converting a multi-objective problem into a set of single objective problems. And we're doing that by varying some parameter values that are the basis for generating subproblems, and the solution of each of these subproblems corresponds to a non-dominated point in the objective function space. Let's have a look at a bi-objective problem to illustrate the epsilon constraint method. Suppose we have two objective functions, f1 and f2, and just inequality constraints. The formulation transformation parameters, instead of objective function weights, these are going to be bounds on the constraints that used to be objective functions. So we need a set of bounds, and we need NP, different values for bounds, if we want NP non-dominated points to result. So this will allow us to formulate and solve NP subproblems. Here's the first subproblem. Here we're choosing f1 as the objective function. And then we take f2 and we put a bound on it. If we are assuming negative null form, we're minimizing the objective function and we have inequality constraints posed this way, then this is how we would put an upper bound on f2. Think back to visualizing in the objective function space and the conflict between objective functions. We want to reduce f1, but that could come at a cost in degrading f2. Basically, what we're doing here is we're placing an upper bound on f2, preventing us from degrading it any more than the limit. So suppose epsilon 1 is the value that we chose to produce subproblem 1. And also remember, this is negative null form. We have to write the constraint such that if it is less than or equal to 0, it's satisfied. But it's a little more intuitive to think of this as f2 must be less than or equal to epsilon 1. Then we vary what the value of epsilon is. We get another subproblem, and so on until we get to the last value of epsilon. Let's visualize this in the objective function space. The objective functions that are converted to constraints limit how far the retained objective function can be minimized. So for example, minimize mu1 subject to an upper limit on mu2. Let's go back to this example where we have a non-convex region in the Pareto frontier. Suppose this is the first value of the bound for mu2. We're putting an upper limit on mu2, and we're going to then try to minimize mu1. Suppose this is the starting point during our optimization, and when we view starting points or other points in the objective function space, it's easy to get tripped up. It's important to remember that this is a distinct visualization from what it looks like in the design variable space. And so the path that we move through as we search in the design variable space might show up as something completely different in the objective function space. We could even skip around different places. The trajectory that we take could be very different from what we might expect a gradient-based method to take in the design variable space. This is the result of evaluating both objective functions at our starting point, x0. And suppose we start there, we apply a gradient-based optimization method, and we minimize mu1 as much as possible without violating mu2 needing to be less than or equal to epsilon 1. So this is then the point that we arrive at. Let's change the bound. We increase it to epsilon 2. Here I'm indicating that we're using the same starting point. And then we get a new value. Here we've relaxed the bound. We've allowed additional degradation of mu2, but that has gained us a reduction in mu1. Let's do it one more time. We have epsilon 3, and we solve the problem, and we get a new value in a new point in the objective function space. Notice that the spacing produced by the epsilon constraint method in the objective function space is not necessarily going to be uniform, even if the distribution of epsilon values is uniform. It depends on what coordinate we've converted to be the constraints that we are varying. So here we were varying mu2, and if we were varying the bound on mu2 in a uniform way, because the slope from that perspective of the Pareto frontier is really steep over here, we're going to have some big jumps, and we're going to have it spread out more in this direction. If it is flatter, then we're going to have some clusters. How might we find the range of bound values? We don't know ahead of time what the Pareto frontier looks like. We don't know what the attainable set is. We don't know what the anchor points are. How are we then going to choose appropriate values for our objective function limits? This is one of the hardest questions to answer at the beginning of solving a multi-objective optimization problem using the epsilon constraint method. I'm just going to talk through briefly one possible strategy. First, choose a very large value for epsilon. Suppose here we choose it large enough that it's not going to cause us to go below the attainable set. We want to make sure it's big enough that there's at least some attainable point below this bound. Then solve the subproblem. Suppose here is our starting point in the objective function space, and we solve the subproblem, and this bound on mu2, it doesn't come into play at all. And so it's just as if we were minimizing mu1 while ignoring mu2. And that's sort of like setting the weight for mu2 using the weighted sum approach to 0. And then that's going to give us the anchor point m1. After we solve the subproblem, so the next step is to reduce epsilon significantly. We want to keep moving this down, solve again, and again we get the same anchor point value. And then we repeat this. We keep reducing this bound until we start to see a degradation of mu1. So in other words, think about this. Move this red line down until it pushes us to require a larger value of mu1. So if we iterate and go here, we solve the problem, then this finally moves us away from the anchor point. Let's go through a few resources for learning the epsilon constraint method. One early introduction of the epsilon constraint method is found in this particular article. Here's the citation for it, and this is available on the course website. A more comprehensive treatment of the epsilon constraint method is found in this textbook, and this is available as an ebook through the U of I library as long as you log in with your library credentials. Also, you can have a look at section 1.2 from this master's thesis, and it includes a review of multi-objective optimization. This can be found on my research group's publications page, and there are actually several other articles on this publications page that treat multi-objective optimization in some detail if you're interested. Let's have a look at a specific example problem. This is a Matlab example out of the textbook. Here we have two objective functions. We have a very nonlinear inequality constraint, and we have some simple variable bounds. Both x1 and x2 have a lower bound of 0 and an upper bound of 6. This is really a simple contrived example. It is very useful for visualization, but it has a really unusual property in that we have defined our objective functions to be equal to the optimization variables. So this is not something that typically corresponds to a real engineering design optimization problem, but it's really nice for visualization purposes. The Pareto frontier, as a result of this definition, is actually where the constraint, this nonlinear constraint, is equal to 0. So you could use this approach. If you need to design an optimization problem that has a particular shape for its Pareto frontier, you can use this approach. You just need to find a function, g of x, such that it is equal to 0 along a curve that defines the shape that you want. What would the Pareto frontier look like without this inequality constraint? What if we crossed it out? What would this problem look like? Let's think about the objective function space, mu1 and mu2. We're trying to minimize mu1 and mu2, but each of those are equal to x1 and x2, so we're minimizing x1 and x2, and we're only now abiding by these simple variable bounds. So we have a lower bound of 0 and an upper bound of 6 along both dimensions. And this is going to be the attainable set because we're looking at the objective function space, but because mu1 and mu2 are equal to x1 and x2 respectively, this also defines the feasible set in the design space. So it's a little bit weird, but if we are trying to minimize both mu1 and mu2 simultaneously, what do we get? Think about the weighted sum method or the epsilon constraint method. As we vary the parameters, say with the weighted sum method, as we vary the slope, what results? What non-dominated point will result? In all cases, this is the only point we get. The objective functions do not conflict. So the multi-objective optimization does not make sense without the inequality constraint. We defined a few minutes ago what a degenerate multi-objective optimization problem is. This is a specific example of a degenerate multi-objective optimization problem. So we need to keep the constraint if it's going to make sense. First, let's try scalarization using the weighted sum. We're going to use weights to transform the multi-objective optimization problem into a set of single objective problems. Here's the new formulation. where we've just created this aggregate objective function, and we need to create different values for W1 and W2 and loop through those and solve the resulting subproblem until we generate a set of non-dominated points. And also remember, we only need to vary one parameter for this because we require that the sum of W1 and W2 is equal to 1, and then we just vary one of these between 0 and 1. Then that is going to be sufficient. It's going to allow us to explore all possible slopes for the ISO cost lines. What if we perform scalarization using the epsilon constraint method? Suppose we choose mu1 as the objective function to retain, and then we add a constraint on mu2. Also, I should note here that this is not in negative null form. It's written in a form that's a little easier to understand. We're going to go through a Matlab example where we demonstrate both of these methods on the same problem. We're going to observe convexity or non-convexity in this problem. And if you remember the nonlinear inequality constraint, that's quite nonlinear. And having such a nonlinear function gives us opportunities to produce Pareto fronts that have non-convex regions. The code for this is up on the course website. It's also up on MATLAB Central. When you are working on homework sets and the project, please remember to use the epsilon constraint method unless you're told otherwise. Here's a screenshot of the MATLAB Central submission for this code. You can download it using this link. Let's switch over to MATLAB. If you download the file and open it up, it's a zip file, and you'll get all of these M files and also a text file. This text file, it's a README. A lot of submissions have these, and this is a good thing to go through first before you start trying to understand the code. So this just explains what it is. This is an example problem from chapter 4, and we're going to use both the weighted sum method and the epsilon constraint method. And here it gives instructions for how to do that. So to use weighted sum, just execute that file. To use epsilon constraint, use that file. And then there's a summary of what is shown using these examples. Let's start off using the weighted sum method. I'm going to open this up and talk through this. So here are some of the standard things that we usually do. We clear the variables, clear the screen, close the figures, and then we initialize the problem. Here's our starting point in the optimization variable space. We have our upper and lower bounds. We set our optimization algorithm options. We create our weight vector. So this is part of what I meant earlier about us only needing to sweep over one parameter even though there are two weights. So how do we do this? Well, first I'm specifying I want 50 non-dominated points. And in other words, I'm going to produce 50 distinct sets of weights. And here I am defining the minimum and maximum value of the weight W1, 0, and 1, and then I'm defining an array W1 that starts at the minimum value, ends at the maximum value, and then we do a little bit of algebra to figure out what the increment in between each of those values should be. The way I use this works with how I've defined the objective function. Notice down here in the for loop where I call fmin_con, after the options struct, I am passing in an extra parameter. And if you've not seen this yet before, be sure you go through the MathWorks page on passing in extra parameters for optimization functions. It's an important technique for you to use, whether for these multi-objective optimization problems or scaling. It just comes up many different places. You need to be able to pass in extra parameters. If I go back and open up the objective function, here we have a second input argument. This is what happens when we pass in an extra parameter after the options struct with fmincon. It then requires us to define the objective function such that it has another input argument for this extra parameter that's being passed in. Then I calculate mu1 and mu2, and that's simply equal to x1 and x2. And then here is where I use the requirement that the sum of the weights be equal to 1 to solve for W2. So this is where we reduce the number of parameters that need to be swept over, and that simplifies this problem. Then we just calculate the linear combination to form this aggregate objective function. Let's go back to the weighted sum code. Here I am initializing xopt. Xopt is a vector, or a matrix rather, where I'm going to be storing the optimal values of the optimization vector as we sweep through the different values of weights. I'm initializing it using the zeros command and setting it to be an n by length x naught matrix. And this is going to then allow us to store all of the values corresponding to all of these distinct weights. One reason to do this, to initialize it, is it allocates memory for this variable, and that can help speed things up. We go through this for loop, going through 1 through n, where n is equal to 50. After that, we can do some visualization. Here I pull up figure 1, plot what the variables are, add some labels, and I've added a breakpoint down here so that we can visualize what those points are first, just the points and no other features in the objective function space. And then after we do that first, then this next plot command, this plots the constraint function, where the constraint function equals 0, which is the definition of the Pareto frontier. And with that, then we can see what the Pareto frontier should be and compare it against the points that we obtained using the weighted sum method. I'm going to click run, and it's going to go to the breakpoint. We can see it ran successfully. We're paused in the debugger. I can pull up the figure. We can see here we obtain many non-dominated points. The spacing is definitely not even. A lot of them are clustered over here. But then we have a huge gap. We don't know what's going on in between. And here we have more points. They're not as tightly clustered, but there's a huge region where we just don't have information. And it looks like we're missing non-dominated points. And we can tell that because there's a gap not only across mu2 values, but also across mu1 values. It is possible to have disconnected Pareto frontiers, but typically we will have Pareto frontiers, even if they're disconnected, we're only going to have a gap across one of the dimensions. Let's keep running and see what the Pareto frontier actually looks like. Yeah, we've traced through. We actually solved the problem quite accurately for all the points we did find, but this is a non-convex region. The weighted sum method is not capable of finding non-dominated points in this non-convex region. I'm going to remove the debug point there, and let's open up the epsilon constraint function and talk through that. The beginning is pretty much the same. Here we are specifying again 50 non-dominated points, but instead we are specifying what is the minimum bound value and the maximum bound value. Instead of just varying the weights from 0 to 1, we actually have to know what reasonable values are for this particular problem. It depends on which of the objectives we can convert it to a constraint, and also what reasonable values are for that objective function. We went through a possible strategy for determining these values if you don't know through some other means. In this problem, we have bounds on the variables, and the objective functions are equal to the variables. So we have these bounds already defined for the objective functions between 0 and 6. So here I'm just using these bounds. But in a more typical practical problem, you're going to need to do some work to figure out what the min and max value is for the bounds. Here I'm defining an array, EPS, that sweeps through all of these values between 0 and 6 using a total of 50 points. Here we solve in a for loop the scalarized problem again using fmin_con. Instead of passing in a weight, we are passing in the ith bound defined in the epsilon vector. And then after we obtain that, we're going to pull up figure 2, plot all those values, and again plot what the Pareto frontier is exactly for comparison. I'm just going to click run, see what happens. Much better. We found a lot of points in this non-convex region. If we are varying the bound for mu2, we are uniform in our distribution when projected on the mu2 axis. But because of the slope of the line right here, we are getting far bigger gaps between points in this region. We could alternatively, if we wanted to fill in some of these gaps, we could use a different formulation where instead we use mu2 as the objective function and we vary bounds on mu1. And we could just add some points where we need them to fill in the gaps. So that's one strategy if you need some information that's missing from your initial epsilon constraint solution. Okay, that is the end of this example. That's all I plan to show for this introduction to scalarization methods for multi-objective optimization. Thank you.